Newton's method. What is Newton's method? The big idea behind Newton's method is, so instead of important question, I'm just going to say this is our big idea here. Okay? Newton's method is an iterative method. I know I'm using the word method in my definition for Newton's method. For approximating roots. Okay? Using, guess what we're going to be using? Derivatives, right? Using derivatives. So what does that word iterative mean? What? Yeah, you repeat it. I'm going to do this over. I'm going to do the same process over and over and over again until I get until I get an accurate enough result to where I'm happy. Yeah, that's pretty much kind of how it works. So sometimes you'll have like an error tolerance that you'll be working with. A lot of times computers have this programmed into them, or calculators have this Newton's method programmed into it with a specific error tolerance that tells them when to stop. And that's the idea of iterative, is you just do it over and over again until you call it good. Okay? So, for example, x to the fifth plus 8x to the fourth plus 4x cubed minus 2x minus 7. There's no nice formula that'll let us actually solve for my roots. If I set that equal to 0, there's no process that I know of to let me actually solve for that by hand. Okay? My only possibility is estimating what these roots are, estimating where it actually crosses 0. So let's take a look at this. Let's look at this graphically so we can kind of understand what's happening. Okay, so let's say I have some function. We'll let this go into the negatives because we are looking for roots, right? So let's say I have some function here. So there's my f of x. And I know it crosses the x-axis at some point here. So we would call this the root. This is where f of x is equal to 0. But if I don't have a process for solving this, then I don't know where this actually is. So what do? Well, what I can do is I can pick an x value close. We're going to call this x sub 0. And what would a derivative help me with? Using a derivative, what can I do?
Differentiation values.
A what?
I can't remember what it was called.
That one thing that we've used before? Yes, it is something we've used before. A linear approximation, right? Or a tangent line. That's another way you can think about it. I can draw a tangent line here. I can find a linear approximation for the function at this point, which is effectively, right, just creating, that's not the best tangent line in the world. But I can create a tangent line at this point. Okay.
Where it crosses the x-axis.
Ooh. So okay, wait. You're onto it here. So if I pick some, let's see. I can create a linear approximation centered at that x sub 0, right? So f prime of x sub 0 times x minus x sub 0 plus f of x sub 0. Right? And, like Romeo was saying, what can I look for? I can look for where the linear approximation hits 0. Okay? I can look for that point where the linear approximation hits 0. So, And notice how it's pretty darn close. So what I'll do
Does it have to be on the right side of the real root?
is I want to see No, it doesn't have to be. Depending on the situation, it could be on the other side of the root, right? It just depends on what your tangent line ends up looking like. So like Romeo said, I want to look for where this approximation hits 0, where its y value equals 0. So you'll notice that if I solve this, I can actually solve this mathematically. I can say, okay, let's let this linear approximation equal 0. I'll subtract f of x sub 0 over to the other side. Oopsies. Not yet. And if I'm solving for x, right, I want to know what x value this is. Remember, x sub 0 is a set value. It's something that we've already chosen. So we're solving for x here. I'll go ahead and divide by f prime of x sub 0. And I'm left with so then I can just add x sub 0 to both sides, and I'm left with x sub 0 minus f of x over f prime of x, x sub 0 equals x. So I can mathematically solve for that new x value. And like we said, that becomes my next guess. Remember, Newton's method is iterative, which means we can do this repeatedly. We can do this over and over again. So what does my solution become? Like I just said, it becomes my next guess. It becomes x sub, what we call x sub 1. So that becomes x sub 1. So, if I want to get this more accurate, now what do? Right, I'm going to do the same exact thing. I'm going to make a linear approximation, but now instead of being centered at x sub 0, I'm going to center it at x sub 1. And the closer and closer I get to my real root, the more accurate that linear approximation is. Remember, we talked about this back in 4 point whatever it was when we did linear approximation. Linear approximations are only accurate if you're choosing x values that are close to your close to the point that you're centering it at. So the closer I get my guess to the actual root, the more accurate my approximation is going to be. Okay? So that's this idea of Newton's method. Okay? So this is, if we were to summarize Newton's method into a single equation, here it is. So Newton's method. The idea of Newton's method is if you want your next guess, we'll call this x sub n plus 1. If I want my next guess of what this root is, then I'm going to take my previous guess and subtract this, the function value at that guess divided by the derivative at that guess. And hopefully you can see how that matches what we got when we actually set it equal to 0 and solved, right? Where does this formula come from? It comes from that process we just walked through over here of take your linear approximation, set it equal to 0, and solve for what that x value is. Okay. So that's Newton's method. Okay, so let's try this out. Okay. So we had that example of x to the fifth. Sorry, I'll leave it like that. We had that example of x to the fifth plus 8x to the fourth plus 4x cubed minus 2x minus 7. And let's see if we can figure out where the actual root is. Okay. Notice, what does it give you? It gives you the initial guess. So that's kind of nice. You don't have to stress about picking an x value that's close to it. It gives you an initial guess of 2.
Will that happen on a little test? Will it give us that funny little...
Yes, and I'll tell you, and we'll go through why that guess is so important. And so because it's so important, yes, that initial guess will be
I don't
given
know
to you.
how-
Yeah, you're good. Okay. Okay. So let's try this out. So if I want to know my next, if I want to figure out what x1 is, my first approximation of what the root is, how do I do this? Right? I can just follow along with my Newton's method formula. So if I want my next guess, I'm going to do my previous guess, which all we have so far is just that initial guess of 2. So I'm going to do 2 minus. Okay. Now what do I need? Right, I need the function value at 2. So I need to know what the function value is at 2. Well, let's see. What's f of 2? I get 2 to the 5th plus 8 times 2 to the 4th plus 4 times 2 to the 3rd power minus 2 times 2 minus, that's a minus 7. So that's just the function value at 2, and you end up with 181. Okay? What do I divide that by? The derivative value at 2. Okay? So that means I need to find the derivative. I get 5x to the 4th plus 32x cubed plus 12x squared minus 2. Everybody okay with that derivative?
If you say so.
Any questions about that derivative? What do I do with that derivative? Plug in 2. Let's see what we get. I get 5 times 2 to the 4th plus 32 times 2 to the 3rd plus 12 times 2 squared minus 2, and you get 382. You guys can all check my math later. Okay, so now take a look at what happens. We get 2 minus 181 over 382. And that gives me approximately, it says keep 8 decimal places, so that's what we'll do. 1.52617801. So there's 8 decimal places. Okay. So, what does this represent? This represents a more accurate guess of where that root is. So it turns out the root is closer to 0, right? My initial guess was 2, but this is telling me, no, the root's closer to 1.52617801. That's what the root's closer to. How do I make it closer?
Do it again.
Let's do it again. Yeah. So if I'm going to do this again, do I want to just use 2 again? No, because I'll get the exact same thing, right? That's just going to repeat everything that I just did. So I want to use my new guess, 1.52617801. Yeah, this one's going to be a lot more decimals than the last one.
Unlimited time.
Yeah. Okay. So minus
F of that.
f of that, which not f that,
No, F
f
that.
of that.
F that.
1.52617801 divided by
F prime of that.
the derivative at this point, at this x value. Right. Very nice. Okay. And once again, I will I'll help you out here. I've pre-calculated all this stuff.
Are you telling us we have to do this on our homework?
Oh yeah. Oh yeah. Okay. The function at that point is about 55.8488742821. That's more than 8 decimal places, but we're trying to keep it as accurate as possible. So I'm keeping as many as I can. The derivative at that point is 166.8306507053. Put it all together, and what do you got? You get 1.19141414. You get that. Okay? Kept 8 decimal places again.
Why Wait, but that's getting like significantly closer to 1 every time. Are we gonna do it again?
No, we're gonna cut.
Okay.
We're gonna stop here. And I mean, unless you guys are having lots of fun. No, we'll keep going. Right. So we're gonna stop there. But what does this tell me? This tells me, okay, no, we're still not quite there yet. The real root is now. This is a more accurate guess of where the real root actually is. Yes, Romy.
So, can you do it so many times to where you start veering off again, or does it just only get closer to the? Exact
Well, no, we'll talk about some different ways Newton's method can mess up. So we will talk about some ways that it won't work. But no, theoretically, if you just keep doing it so many times, you're going to get so accurate that you're not going to see any difference in your answer when you're done.
Places.
Yeah, in 8 decimal places, right. You're not going to see any difference. Okay. So,
Try it and I'll let you know.
let's look at... Let's look at what this looks like. Desmos. Okay. Y equals... Let's get my function out on... Well, we might not have time to look at the graph of this. I don't know. Especially with how long it's going to take me to plug everything in. So we're just going to keep going. Sorry. That's what happens when I go through a homework problem at the beginning of class.
Yeah. Whoever asked that question knows.
Speaking of which, this is a great time. I don't want to miss... I realized I never told you guys a joke on Thursday. And I almost missed it again.
Or it's more like
Yeah, right. So I got to tell you one. What do you get for getting old? For growing old? What do you get for growing old?
arthritis. Dementia.
A trophy. Or atrophy. Okay. Don't worry. My second one's a better one. Let's see. Joke number 2, the real joke for the day. Here we go. I just found out that the company that makes yardsticks won't be making them any longer.
Oh.
That's a good one. Okay. So where can Newton's method be nice? Take a look at this example. Let's use Newton's method to approximate square root of 2. And notice using x sub 4, which means, hey, I want to do 4 iterations of this. Not just 2. Let's do 4 iterations. I don't know if we'll get all the way to the 4th iteration. Or maybe I'll just shortcut it. Okay? So, but wait. I thought Newton's method was about finding roots. This isn't a root. This is a square root of 2.
Square root.
Oh.
Square root.
Walked right into that one.
He said it.
Okay. This is a square root, not a polynomial root. So how can I still use Newton's method for this?
You're not listening.
How can I still use Newton's method? Yeah, Adam.
It's like the equation of the root of x and then x of 0 is 2, so that's like, you're just kind of, you can solve for any point on the graph of...
Because you're thinking, let's let my function equal x. But my problem with letting my function equal x is, remember, Newton's method is all about finding where the function equals 0. Where is the square root of x equal 0? It's just 0. So Newton's method won't help me find the square root of 2 if I let my function just equal square root of x.
So wait, is f of x equal to this square?
Yeah, instead, what could I set my function equal to? Right? I don't give you a function here. So what can I make my function? What function, square root of 2 is just a constant function. What function will have a x-intercept or a root, right? What function will have a root at square root of 2? X plus square root of 2. No, that'll have a root at negative root 2. But the problem about doing this is this function requires me to know what the square root of 2 is, which is the whole problem, right? Is we're trying to approximate it. So I like it. Good thought. But it's kind of circular reasoning. Okay? Other thoughts? let's see, square root of 4. Square root of 4 is nice because we know that it is. But once again, I don't want to let my function be the square root of x because the square root of x has a root at 0. Aha! What if I did this? By doing that, it doesn't require me to know what the square root of 2 is. And if I solved for that, if I set this equal to 0 and solved, what would you get? Aha! So this function has an x-intercept at the square root of 2. But because I use the squared term, I don't have to know what the square root of 2 is in order to graph this function. Okay? So now I can use Newton's method. Okay? This is where the root's obviously not 2, right? Square root of 2 is not going to equal 2, but we can use it as our first guess. Sure, let's use it as our first guess. Okay, so x sub 1 is equal to 2 minus, what's the function value at 2? 2, right? Because you get 2 squared minus 2. Remember, yep. Derivative. What's my derivative of the function? Just 2x. So what's the derivative at 2? 4. And I get 2 minus 1/2 is just 1.5. Okay? Let's do it again. Iterative. X sub 2. I'm going to do 1.5 minus the function value at 1.5. Well, that gives me... here, I'll just do this for now.
0.2.
Derivative of 1.5 is nice because that's just 3. But plug that in. You should get... I'll let you guys...
Are you still doing 8?
Well, this one actually repeats, doesn't it? Should get 1.416 repeated. Okay, very nice. I'll let you guys do the next one. See if you get the same thing I got.
I have to plug in a bunch of 6s during the calculator.
just a bunch, right? Just to keep it as accurate as possible. There you go. Okay. Hopefully you guys have come up with something here. You should have gotten 1.41421. Is that a 5? I can't read my own handwriting. 5686. Dot. We good? Any questions about where I got that from?
Hey, that's what I got.
Sweet.
I got like slightly off by like 0.0002.
Yeah, so that means you did it right. It's just how many 6s you kept. Like when you plug this in. So don't stress too much about
I
that.
got it right.
Don't stress too much about that. Okay, and then if you're just having so much fun doing this and wanting to keep going, your x sub 4 is x or 1.414213562. Notice how close that is to x sub 3. So Newton's method is really effective. When it works, it's really effective. It gets you close to the actual root pretty darn quick. Because even x sub 2, we were already to 1.41 just after 2 iterations. And then, so the third iteration just got us more accurate to the 1000th degree. And then even then, when I went to the fourth iteration, I was already fully accurate up to 5 decimal places. And it was just fixing everything past 5 decimal places. So it's really effective when it works. Okay? It's just lots of decimals. Okay. So let's talk, or any questions about how Newton's method works? Okay. So let me give you another one. What if I wanted to know the cube root of, I don't know, 50? Cube root of 50. It's an irrational number. And we went through some examples like this back in linear approximation, but with linear approximation, we were kind of relying on this number inside the root being close to a perfect whatever we were rooting, right? So is 50 close to a perfect cube? I don't think so. Maybe it's kind of close to 64, which is the cube root of, which is the perfect cube of 4, right? That's 4 cubed. So it's kind of close to 64, but not that close. So linear approximation is really not going to be the best way to go about it. Instead, using this iterative process of Newton's method is going to be a much better way to actually get what my root is. So what would my function be for cube root of 50? Right. I'm going to let the power of my function match what root I'm trying to find. So x cubed minus whatever the number is inside my root. Right. And that's what I use as my function when I use Newton's method. Okay. Any questions about that? Okay with that? Awesome. So now let's talk about what are some ways that Newton's method could possibly not work. Okay? Go ahead and disregard this whole exercises thing. That was just a...
We don't exercise.
No way. No, that's your guys' job. Okay. So first off, remember my Newton's method formula. Let me just put it up here to reference here. If I want my next guess, I do my previous guess minus the function value at my guess over the derivative at my function, or at my guess, right? At my previous guess. Can anybody see where I might end up having an issue?
Yeah.
Where, Suzanne?
What happens if your derivative is equal to 0?
Right. So that's my first possibility. If at any x sub n, the derivative is equal to 0, then we have an issue. So that's the first possible way that Newton's method can fail. And if you think about it, this makes sense. Because what if you're going through Newton's method and you end up and you've got your function, right? Boop, 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 boop. And you end up with a guess that's right here. Right? Here's your x sub n. Notice, what's my derivative? 0, right? I'm working at a local maximum. I've got a local maximum. Well, if my derivative is 0, will my linear approximation or my tangent line ever cross the x-axis? No, which means I'm stuck. I won't get another iteration. I won't get another guess. So that's why this is a problem, because if your guess ever ends up being like a critical point, then you'll never actually reach the x-axis again. Okay, so that's my first issue. Second issue. The approximations may approach a different root. You might end up approaching a root that's not the one that you were actually looking for. Okay? So, let's take a look at an example of this. So let's say I'm working with something like the sine function, where you've got something like this. You'll notice I have multiple different roots. And let's say, yeah, I want to try and find this one. So I'm going to pick my first guess like here. Well, if I draw my tangent line, if I draw my linear approximation, I get my next guess right here. And then if I draw my linear approximation there, look where it's taking me. It's taking me over to the other root when I wanted to find this one. So that's another issue that can happen with Newton's method, is you could end up approaching the wrong root or a different root. Okay. Last. So as we're going through this, think about what can maybe fix these issues, right? Okay, the last possibility of how this can go wrong is the approximations could also just fail to approach anything. Okay. And this one I'll have to show you kind of a more specific example. Because my issue in number 2 was that it was still approaching something, it was just the wrong number. But there's also the possibility of it just not approaching anything. So let me show you this example. Let's let the function f of x equal x cubed minus 2x plus 2. And I know, right, this is a cubic function, so I know it has at least one root. And so, what the heck? Let's try an initial guess of 0. Let's let my initial guess be equal to 0. 0 is a nice number to work with. We like working with 0. So what would x sub 1 be?
2.
We'd end up with 0 minus, let's see, if I plug in 0 to the function, I get 2 over, what's the derivative here? I get 3x squared minus 2. Yeah, so I get a little minus 2 there. So what is 0 minus 2 over negative 2? Positive 1. Right? 2 divided by 2 gives me 1, and then the negatives cancel out and make it positive. Okay? Well, how lucky. I got a whole number for my next guess. Okay. So what's x sub 2? I get 1 minus f of 1 over f prime of 1, which gives me 1 minus, let's see, if I plug 1 in, 1 cubed is 1, minus 2 times 1 is 2, so I get 1 minus 2 plus 2, and just get 1. Okay, if I plug 1 into my derivative, I get 3 times 1 squared, so 3 minus 2 is 1. So I end up with 0. Do we see the problem?
Yeah. You're just gonna keep putting 0 every time.
Yeah, because now my second guess is equivalent to my initial guess. Which means if I plug this in again, what am I going to get? I already know what I'm going to get. I know my next guess is going to end up equaling 1 because it's going to match what x sub 1 was going to be. So if I just keep doing this process, I just go back and forth between 0 and 1, and I'm never actually approaching a number.
So
Okay.
do we just have to choose x sub 0 equals 0.1 or something?
Aha.
That would work?
Right. So what's my solution to a lot of these problems? Choose a better initial guess, right? Because even look at this example. If I just pick something closer, would I have that issue of approaching the second root? No, right? And same thing here. Like Romeo was saying, what if you use 0.1? That would avoid this issue. You wouldn't end up in this back and forth between 0 and 1. You would actually end up approaching a value. So with a lot of these issues, you just have to pick better guesses. Okay? And that's why for a lot of the problems, I'm just going to go ahead and give you the guess, give you that initial guess, so you don't have to stress about these 3 different issues. But if you're doing this like on your own, you'll have to, and you reach a spot like this where you're like going through Newton's method, and all of a sudden you get a derivative that's equal to 0. What do you have to go do? Change your initial guess. Go back and change your initial guess. Okay.
So with number 2, you have to choose an x sub 0 between the 2 critical points. It cannot, because The
Yeah.
x sub 1, it's past
I mean-
the critical point, right? Right there, so where it hits.
Well, no, right. Because I picked my first guess. My first guess was after this critical
Yeah.
point. I just the problem was is that my next guess was on the other side of my second.
So then that's how you know you still need to get closer to.
Yeah. So, because a lot of times, like, if this were like, well, say sine, like, let's say this was my sine function, I know roughly where it should be crossing 0, right? And so if I'm using this to get like an approximation of pi, and I'm suddenly getting something that's like 6 or something, I'm like, wait a second, this is approaching the wrong thing. I need to go adjust my initial guess. So, that kind of stuff. So, let me, how do you, just to summarize here, we've already talked about this, but how do you resolve these issues? Change your initial guess. Or x sub 0. Change your x sub 0. Okay. Awesome. Sorry. Yep, sorry. Oh, yeah. That skipped, huh? I don't know how that happened.
Yeah.
Okay, yeah, that's it for the day. So I think on the homework, I don't think there's very many homework problems to this.
We could have totally
this one. Let's
actually
see.
graphed that. I won't lie.
4 points. Let's look at Newton's method. Yeah. So this homework only has 4 problems on it. So for those of you who are like, we have to do this on the homework. Yeah, you only have to do it 4 times. So that hopefully will make you feel a little bit better about going and doing the homework for this. Yes. What? Yeah, 4.10. There are no guided notes for 4.10. So just come with some paper, and you should be fine. Don't forget the quiz. You guys have a quiz due tomorrow.